Hi all, in 11.3 we are doing inferences about two population means with independent samples. Our objectives include test hypotheses about the difference of two independent population means, and then construct and interpret confidence intervals for the difference of two independent population means. We start with the hypothesis tests and a note. We can proceed with the 5-step process for hypothesis testing, provided that the samples are obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. The samples are independent. The populations from which the samples are drawn are normally distributed, or the sample sizes are large, so both n sub 1 and n sub 2 greater than or equal to 30. And for each sample, the sample size is no more than 5% of the population size, so n less than or equal to 0.05 of capital N, that population, or, as we've thought, 20n less than or equal to that population size. So for our 5-step hypothesis testing then, we start with step 1, determining the null and alternative hypotheses. Recall there are 3 different possibilities. We've got our two-tail, left-tail, and right-tail tests still. Our null hypothesis will be the same for all and is always equality. This mu sub 1 minus mu sub 2 equals 0. Or you could say mu sub 1 equals mu sub 2. But that's how we'll see it in StatCrunch, so I'll write it out that way for all of these. So mu sub 1 minus mu sub 2 equals 0. And for the right-tailed test, again, our null hypothesis is always assuming that those two population means are the same, so their difference is 0. For two-tailed, h sub 1, we're looking at mu sub 1 minus mu sub 2 is not 0. For left-tail, we want mu sub 1 minus mu sub 2 less than 0, or mu sub 1 is less than mu sub 2, so their difference is negative. And for the right-tail, mu sub 1 minus mu sub 2 greater than 0, or mu sub 1 greater than mu sub 2. Note, mu sub 1 here is a population mean for population 1, and mu sub 2 is a population mean for population 2. For step 2, we're determining the level of significance, alpha, depending on the severity of making a type 1 error. Generally, again, you've seen it's been given to us in the problems. But if you were doing your own research, you'd have to pick one. Step 3, verify the normality requirements and compute the test statistic. We'll get a t-score again. Note, we'll use technology, but the calculation is t naught equals x sub 1 bar minus x sub 2 bar over our square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And just like we saw for the proportions, since we are assuming the means are the same, this mu sub 1 minus mu sub 2 is assumed to be 0, so it's not written in the formula there. But that is our sample minus population mean over standard error that we're used to for these z-scores, t-scores throughout the whole course. Where for this one, this x sub 1 bar, s sub 1 squared, and n sub 1 are the sample mean, sample variance, and sample size respectively for sample 1. And x sub 2 bar, s sub 2 squared, and n sub 2 are the sample mean, sample variance, and sample size respectively for sample 2. When computing by hand, the smaller of n sub 1 minus 1 or n sub 2 minus 1 are used for the degrees of freedom, but we'll be using the tech for it, so it'll do its own calculations. Step 4 is to compute that p-value, and then step 5, we state our conclusion. As always, if p is less than alpha, we say our results are statistically significant and reject the null hypothesis. If p is not less than alpha, we say that our results are not statistically significant and do not reject the null hypothesis. So we've got a couple problems to run through to just make sure we're okay with this process as well. So for number 1, IQ scores for a random sample of subjects with low lead levels in their blood and another random sample of subjects with high lead levels in their blood are summarized below. We want to use a 0.05 significance level to test the claim that the mean IQ score of people with low lead levels is higher than the mean IQ score of people with high lead levels. So step 1, we've got our null hypothesis that mu sub 1 minus mu sub 2 is 0. And for our alternative, we want low lead levels to have higher IQ scores. If low lead is sample 1, right, n sub 1, x bar sub 1, s sub 1 there, we've got our mu sub 1 minus mu sub 2 should be greater than 0. All right, step 2, they're giving us alpha is 0.05. For normality, IQ scores are normally distributed, so the sample size doesn't matter there. And there are way more than 78 or 21 times 20 people in the population. So we are good to go. We are still under t-stats, but we're going to do 2 samples with summary here. If you had data, you could just import it from the homework, but I want summarized ones here, so I don't have to type a bunch in. So we have our sample mean. Make sure you're typing these in the right order. Generally, we're given sample size first, mean, standard deviation. So just make sure you're putting them in the right boxes, but 88462. Standard deviation 15.34451, and my sample size for that first group was 78. For sample 2, we got a mean 86.90476, standard deviation 8.988352, and sample size of 21. We don't want to pool the variances ever, so its default is off, which is good. Just leave that. That's assuming population standard deviations are the same, which is not what we're doing. We don't know anything about the population standard deviations. So our hypothesis test, we had a greater than, a right tail test here. We can do that p-value plot just for fun and compute. When we do our computation, we get our t-stat. So t-naught is a 2.282, and our p-value is 0.0132. For our conclusion then, p is less than alpha, right? This is less than that 0.05 we were given. So we reject the null. We have sufficient evidence that the mean IQ scores are higher for people with low lead levels. In their blood. All right, and we can see on that p-value plot, we are more than 2 standard deviations above the mean. We're up in that upper tail with a p-value that's pretty small, the 0.0132. So we have good evidence. All right, our second idea here is to construct and interpret confidence intervals for the difference of 2 independent population means. Our definition, a 1 minus alpha times 100% confidence interval for mu sub 1 minus mu sub 2, the difference in those population means, is given by our quantity x sub 1 bar minus x sub 2 bar plus or minus our error, where our error is t sub alpha over 2 times our square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Note, remember to verify normality if the sample sizes are not large. For two Dutch researchers conducted a study in which 2 groups of students were asked to answer 42 questions from Trivial Pursuit. The students in group 1 were asked to spend 5 minutes thinking about what it would mean to be a professor, while the students in group 2 were asked to think about soccer hooligans. The 200 students in group 1 had a mean score of 23.4 with a standard deviation of 4.1, while the 200 students in group 2 had a mean score of 17.9 with a standard deviation of 3.9. We want to determine a 95% confidence interval for the difference in scores and interpret the interval, and then answer the question, what does this say about priming? So I'm going to put some data in while this is on the screen, and then we can run down and do our setup. But we're going to toSample with summary. My sample mean for the first group, 23.4, standard deviation of 4.1, and we had a sample size of 200. For group 2, we had a 17.9 with standard deviation 3.9 and 200 in our group again. We're going to do a confidence interval at the 95% level and should be good to go, right? We've got large sample sizes, so we're not worried about the normality here. We do want to set up our hypotheses. So h sub 0, mu sub 1 minus mu sub 2 would give us 0. And for h sub 1, mu sub 1 minus mu sub 2, let's say not equal to 0. For step 2, we weren't given alpha. We can just put the confidence interval or confidence level here. All right, we're at 0.95 for that 95% confidence interval. Step 3, we've put in our data already. Stat, t-stats, 2 samples with summary. So we can put our confidence interval here. we've got a 4.71 to 6.29. And so we can see 0 is not in the interval. For our interpretation, we are 95% confident the true difference of the population means is in our interval, or you can say between those two values we found. You'll see it typed out in the homework, and pick the one that is correct, but always remember to start with that confidence. All right, and then if we want a conclusion here, we're kind of interpreting 0 is not in the interval. We have all positive values. So the results suggest that priming may be important. All right, those positive results, we can see the group 1 has the higher mean, right? We have some evidence that thinking about being professor may have helped them answer questions more than thinking about soccer hooligans. And so there's research out there about just, standing with a power pose before you take a test, stuff like that. You can look some up, but priming, getting yourself in that right mind state for the task at hand. But try some out, reach out if you got questions.